Let's talk about how strong electrolytes affect these colligative properties. So they have a stronger effect because they separate into ions, so there's more particles. So we have to take that into account. We're going to use what's called the Van 't Hoff factor, given the symbol I, different than the math I. And that's the ratio of moles of particles that are in the solution divided by moles of formula units that are dissolved. The Van 't Hoff factors are not exactly equal to the expected values because there is some ion pairing. So here we have an illustration of sodium chloride solution. Here's a chloride ion. It's surrounded with water. Here's a sodium ion surrounded with water. But these guys can still hang out together. And if they're hanging out together, then they're acting like one particle instead of two. And so that means that we're not going to get 2 moles of particles for every mole of sodium chloride, as we expect. We're going to get a little bit less, 1.9. K2SO4, right? So here's where understanding these formulas is important, right? K2SO4. Well, that is 2 potassium ions and 1 sulfate ion. So a total of 3 ions for every 1 unit. So we would expect the Van 't Hoff factor to be 3. It's actually a little smaller than that because of ion pairing is 2.6. You do not need to memorize the measured Van 't Hoff factors. You should be able to come up with the expected values, though. So when we have ionic solutions, we're going to have those same equations, but we're just going to multiply by the Van 't Hoff factor. Here's a question: which aqueous solution has the highest boiling point? So adding a solute to the water causes the boiling point to go up, right? These are the same concentration. But this is not ionic, and these two are ionic. So the one that has the highest boiling point will be the one with the most particles. Which one has the most particles when it's dissolved? Well, this, I definitely see why you could think that, because this has so many atoms. But these are not going to separate.
No.
The NaCl is going to make a little less than 2 particles, and this is going to make a little less than 3 particles, right? So the MgCl2 is going to have the higher boiling point. Calculate the freezing point of an aqueous 0.1 molal iron chloride solution using a Van 't Hoff factor of 3.2.
So ionic compounds are always going to be...
Ionic compounds are always going to separate into ions, and so they're going to have a bigger effect. Yeah.
If you have a covalent compound and an ionic one, the ionic one will always have more particles in it?
If the concentrations are the same, yeah.
Okay.
Yep.
Will it always give us the Van 't Hoff factor, or will it cause
So if it doesn't give you the Van 't Hoff factor, then you use the expected Van 't Hoff factor, right? So here, the Van 't Hoff factor is given to us. That's 3.2. The molality is given to us, 0.10. We have to go look up the constant, but I happen to remember that. So 3.2 times 0.1 times 1.86, 0.5952 degrees Celsius. So what is the freezing point? What's the freezing point of pure water? 0.
It's going to be that.
This tells us it's going to go down that much. So the new freezing point is negative. I guess that would round to 0.60 Celsius. Okay. So strong electrolytes also have a larger effect on the vapor pressure. So then when you're looking at vapor pressure of electrolyte solutions, you have to account for the dissociation when you're calculating the mole fraction. We're going to skip that one and talk about this one. So osmotic pressure sounds kind of weird. Osmosis, kind of a weird thing. But the reason that we're covering this is a really significant concept in medicine, right? Dealing with a biological system where all the cells have membranes. If you're going to be injecting things into tissue, you don't want the tissue to be damaged, right? So, you go to the hospital, you get an IV, and they're, dripping stuff directly into your bloodstream. If they put pure water into your bloodstream, it would kill you. Well, but water's supposed to be good for you. Even not in your blood. It needs to have the right ionic strength. It needs to have the correct osmotic pressure. The osmotic pressure depends on the number of particles that are dissolved. So if this is a normal blood cell. It's kind of a little bit like a donut. It's nice and round. It's got this divot in the middle. If we have an isoosmotic solution, meaning it has the same osmotic pressure as the fluid in your body, for a cell like this, the solution inside and the blood plasma outside have the same osmotic pressure. So we don't have net movement of water one way or the other. So it has this nice shape. Now, if your IV is going to be hyperosmotic, it has a higher osmotic pressure, meaning there's too much salt or sugar or something in it, that's going to draw water out of the blood cells and cause them to shrink up and get kind of spiky like this. That's called crenation. If you have a hypoosmotic, too low of particles, then it's going to cause water to go into the cells, and they're going to bulge out like this, and they'll keep doing that until they burst. Also, not good. So, isoosmotic, also called isotonic solutions, are critical for intravenous solutions. In class yesterday, I had a student who was at a facility where a nurse injected the wrong thing into the IV. It was water instead of normal saline, and the patient died. Yeah.
It's all this blood, right?
Well, your cells blow up, yeah. The cell walls burst, and then the cells don't work anymore, and then you don't live anymore. It's very tragic, yeah.
And then if we drink water, what's our body
That's a great question. So then what happens when we drink water?
It doesn't, that's two different, it doesn't come with those two.
Yeah, so that's not going directly into your bloodstream, so it's not going to cause your blood cells to burst. But it does go through your intestines, and your intestines will absorb water because they have higher osmotic pressure than the water that you're drinking. And that's the good way. If you're drinking salt water, that's hyperosmotic. It has higher osmotic pressure, and that's going to pull water out, right? So if you get water coming in, right, and your body's like, you had too much water, it has a way of getting rid of that, right? It'll just send it to your kidneys and you'll pee it out, right? But in intravenous solutions, yeah, really bad, really bad. So what's called isotonic saline, also sometimes called normal saline, it's a 0.9% mass to volume ratio, 0.9 grams of sodium chloride per 100 mils of solution. And these types of units are real common in medicine. So why don't they use molarity? Well, they don't care how many moles there are. They care about, how do I make this solution? So this one's easy to make. You weigh out 0.9 grams of sodium chloride. You have a container that will hold 100 milliliters. You put the salt in there, you fill the container with water, done, right? It's not like a molarity where you would have to calculate the mass to use, right? So, medicine.